Dear students, let us begin lectures on machine design part 1. This is lecture number 17 and the topic is design of threaded fasteners. Now in the last lecture, that is on lecture number 16, we have learned different geometrical profiles of different kinds of threads. And now threaded fasteners, as we have discussed, they are very useful, and in many machine parts the parts are joined together by means of threaded fasteners. So design is very important for this kind of machine elements. In this lecture we are going to learn how to design such a threaded fasteners. Now let us come to the design. Now the design will depend on definitely on the material selected for the fasteners. So these are what you are seeing is a list of the screw materials. Now the screw materials will be chosen depending on the application temperature of the applications. Now the room temperature applications, the materials are low carbon steel, this is for the light structure, and maybe medium carbon steel, but it must be heat treated. There are various processes of heat treatment, and these are all specified in standards. So when you have to design such a threaded fastener, so you'll have to look into the standard. There are different material standard, and the medium carbon steel with different kinds of heat treatments are possible. Quenching and tempering, these are the two most useful, that is most frequently used heat treatment process. For the high temperature, the alloys are used. Now titanium based alloys are used for high temperature. Then as the temperature goes high, then we use martensitic chromium steel. Here the chromium is added. Then Inconel, for a very high temperature, Inconel and super alloys are to be used. So this information is very much essential in order to design a threaded fasteners. For any design, we first need the informations about the materials, because everything will be designed based on the material properties. So these are the materials used for the screws and fasteners. Then comes the strength of the bolts. Now strength of a machine element is not the same as the ultimate stress of a material, because this is the strength is the property of the element. Now there are standards specifying the strength. The metric standard specifies the strength, the bolt strength, according to different property class of materials. There are different property classes of materials, namely ISO grades, and for different property classes we have the bolt standard specified. The standard in any design handbook, in the standard you will find there are two things. One is minimum yield strength and minimum ultimate strength. So when we have design any bolt, then we must see that the minimum yield strength is satisfied and minimum ultimate strength is obtained. So these are again very important considerations for the design: the bolt strength as well as the material selected for the bolts and nuts as well and screws. Now then we come to designing a bolt. Now the design of bolt will definitely depend on in which application it is used. So there may be a case where the loading is normally static. Static loading means that it doesn't vary with time, or it varies very slowly with time. It starts from 0 and reaches one steady state value after a long time interval. So this is the static loading. In static loading, there may be cases where the pre-stress is applied and where the pre-stress is not applied. We are going to discuss separately these two, where the pre-stress is applied and there is no pre-stress. And there may be the loading where the loading varies in cyclic manner, or it will have a fluctuating loading. Take for example one foundation which supports, let us say this is the foundation which supports one machinery which contains some rotating elements. So, this is a motor, for example, which rotates. Now, definitely there will be some unbalance in the motor because of the manufacturing defects. So, and this motor is bolted to the ground. Now, as it rotates, so there will be a fluctuating force developed, and if you find out the free body diagram, the normal stress here on each of the bolt will have a fluctuating component. So, if you plot F against time, then you will see the variation looks somewhat like this. So, this is fluctuating stress. Then there may be other situations. Let me give you one more example. The situation where, so this is, let us consider the connecting rod of a crankshaft. So, this part goes to piston, and a bolt is applied here, a bolt is there, and this part goes to piston. And now all of us know that in the piston, whenever the engine operates, the force developed on the piston becomes, say, somewhat like this, a very cyclical fluctuations, but that force will always cause some fluctuating component in the bolts. So, there are various cases where the machine parts will have fluctuating forces. Normally machines are made to transmit power from one source to the other, to transform and transmit power, and definitely there will be some movement. So, whenever there is some movement, there will be always inertial forces and definitely some other fluctuating forces. So, these fluctuating forces will be transmitted from one joint to the other through these bolts. So, bolts definitely, or the joint members, will be subject to the fluctuating forces all the time. So, definitely that is very important thing to consider for while designing a bolt. We are going to study some design criteria for variable loading. There may be cases where the loading is impact. So, this occurs, for example, in punching machine, where the impact occurs. Definitely the bolts connected for various parts will also experience some impact load. Now, static loading without pre-stress. Here we see that we are going to study in some more details, but what is important, that whenever we have a static loading without pre-stress, then the bolts must be designed such a way that the bolt does not break under tension. So, it is possible that the bolt may break under tension. The threads are not crushed. So, there will be bearing stress across the thread, and that may cause the failure of the thread. So, threads may get damaged. We are going to avoid that by proper designing. The threads do not fail by shear. So, this is one mode of failure where the threads may fail by shear. The roots will have adequate strength to sustain the shear stress. So, these are the few important things, failure modes, which we have to consider. Let us now come to one example, design example. Let us consider a case where an I bar is used to lift a load. So, here what I am drawing and this is the threaded member, and here we have a nut. Maybe we have to extend this. So this is nut, and a load is applied here. So this carries a load. Definitely here there is no pre-stress, and these are used for the lifting certain load. Now let us consider this screw. What happens to this screw or this bolt, that it is subjected to tensile force. So when let me draw the screw in a so this one, ultimately this is the part connected to the nut. So and there is a pressure force here. So therefore what happens is that if you consider this part, it is subjected to a tensile load. And what will be the tensile stress developed? The tensile stress is definitely sigma is equal to P divided by A and the area of cross sections. Now what is the most vulnerable sections? That is definitely here the root area. There are few areas specified when you look up at the table. So one is the root area, so that is this minor diameter. If you remember, this is the area corresponding to minor diameter. So this, let me call it as AT, which is the root area of the thread, and so this is the maximum stress developed, and this must be less than sigma allowable. We know all sigma allowable is sigma ultimate or divided by factor of safety. Now we will have to choose AT such that, given a force P, we have to choose AT such that this condition is satisfied, and we know that AT is pi by 4 d let us say dc square, where the c is the chord diameter. Now we select the chord diameter, and then in the table we find out what is the root area, that is chord diameter, and then we select the next higher size of the thread. So this is how the thread is selected here. Now there are other modes of failure, as we have mentioned in the last slide, that is the shear failure as well as the bearing failure, that is a crushing failure. Now we see that the force between this nut and the screw here, or nut and the bolt, it depends on various factors. So let me draw the scaled way. So this is, let me call it, this is the part of this screw, and the other part is corresponding to the nut. So this is for the nut. So definitely there will be the clearance between the nut and the thread and threads of the bolts. So this clearance, again, it will also say what will be the total area of contact, and this is the area of contact over which the bearing pressure will act. But this is very complicated for analysis, so we have to make very rough estimate of that, because the rough, why rough? Because we can provide adequate factor of safety such that the bolt doesn't fail even if we have a very rough estimate. That is, even if the design details are not very accurate, but with a large safety factor we can of course make the design quite safe. Now, what is the simplifications in design or in analysis? The simplification is that the forces are uniformly distributed. So, if you draw, so if I consider this to be something like the screw profile, of course I have not drawn the taper and the exact thread geometry, but for rough estimate it does not matter, and the force is acting over here. So, on each surface there will be forces. So, if there are n such threads, then the total force acting per thread is P prime is equal to P divided by N, and this is uniformly distributed. So, then what will be the total bearing stress? Sigma bearing will be P prime divided by the area of cross section, area on which the force is applied, and that is equal to this area. If you take this total this is the total disk. So, this will be equal to pi by 4 d outer or d major square minus d minor square, and sigma bearing, it must be less than the sigma compression allowable. Now, here from this we can find out what are the values of minor diameter and major diameter, etc., etc. Given one diameter, we can find out what will be the other diameter, that is the width of the or the height of the thread. Now, it may seem that if we increase n, then sigma b goes down, because if you see that if you increase n, P prime decreases, so therefore sigma b decreases. But this is not in fact true, because here the analysis is so simplified that it is hardly realized in practice. What happens is that when the first few threads where the contact first appears, that is here. So, this is the screw profile and this is the nut, let us say. So, this is the nut. Here we apply, suppose, the force P. So, here what is normally observed is that the first few threads, first 2 or 3 threads will take the lion's share or the majority of the load. The other threads, as we progressively go from this side to the other side, these directions, then the load taken by each of the thread will be very, very small. A nonlinear distribution is actually observed, where the load taken by the first thread is almost 37%. This is 37%, and it decreases very fast, and beyond 6 or 7 threads it hardly carries any load. So, here this assumptions that this load is uniformly distributed over the cross sections as well as over each thread is not entirely justified, and we will have to make more elaborate calculations. So, here what we normally do, we take n equal to 1, but we take this load to be 37% of the entire load. So, we calculate based on a single thread which takes 37% of the load. So, this gives fairly good results. Then there is another mode of failure, which is the shear failure, and if you see that the thread this is the thread where the force is acting, and if you make the same assumptions, that is each of the thread will carry a force P prime, and now this behaves like cantilever beam, and therefore the shear stress here on this sections, which is the plane for maximum shear, the shear stress will be P divided by, so tau is P prime divided by the area. Area is this height, so pi dc times this height h, let us say. So if we have a large h, then the shear stress is less. Therefore the BSW thread, which has a very large value of h, it has a great root strength, as we have discussed in the last slide, but here the analysis also confirms that. So here tau must be less than tau allowable, and tau allowable is roughly equal to sigma allowable divided by under root 3. This is these are the major stresses experienced by a thread in a bolt. So there may be there are tensile stress as well as compressive stress, again the shear stress. So we can have, when all the types of stresses are available, then we can use the failure formula, that is von Mises theory of failure, which says that you will have to calculate the sigma equivalent, which is equal to sigma square plus thrice tau square, or you can take tau max, which is equal to sigma by 2 under root square plus tau square. Now here sigma prime must be less than sigma allowable, and this must be less than tau allowable. This uses the maximum shear stress theory, whereas that uses the von Mises theory of failure. So this is how a bolt is to be designed when there is no pre-stress. Now let us see what happens when there is pre-stress. Now whenever there is a pre-stress, then we have certain advantage. We are going to see what are those advantages in some more details, but here what is mentioned, that the advantage of pre-stress is to relieve the bolts partly from external load. So we will gradually see what are the advantages, but here now see what the methods of pre-stressing. When we have when we want to pre-stress, then there are few methods. One very well justified method is the torque wrench method. What we use a torque wrench which gives a measured value of torque. The turn of the nut method is just the method where we just first tighten the nut by hand, that is, it is hand tightened, and then we give a few turns by means of wrench. Now how much turn is to be given, that is calibrated, but the calibration technique is quite complicated and we are not going to discuss here. There are other various advanced techniques like hydraulic stretching, etc. Normally it is very difficult to find out what will be the pre-stress value, but based on some empirical relationship, that is some experimental results, we can get that this initial value, initial tension is equal to 2840 D, where D is the diameter, nominal diameter of the thread of the bolt in millimeter, and this is in Newton. So normally this initial force is given. In the next slide we are going to see how does this pre-stressing help in relieving the bolts from the external load. So let us consider the case where one cylinder cover is bolted. Here there is this is the cylinder cover, and this is part is the cylinder, and this is used for containing some pressurized fluid. So therefore this must be leak proof, that is we must have a gasket here. So this is known as gasket, and this is bolted. So you use a bolt over here. Now we tighten it. The load taken by the bolt is now will cause some initial tension here. As you can see that whenever we tighten, then if you consider the free body diagram of this cover plate, then as we tighten it by giving some torque, then what you see here, the force is here, it presses, and the gasket also initial force. So the gasket also gives a pressure. So if you draw the free body diagram of the bolt, then it looks like so there is F initial and F initial over here. So this causes initial tension. Now this tensile force is again increased if we apply external load here. So now what we are going to do, we apply F external on this cover plate and see what happens. The cover plate, when we apply external force here, then the bolts, there are different bolts, there are a number of bolts equally spaced along the periphery of the along some circle of on the cover plate. If you draw the top view of the cylinder, then what you see, so if this is a cylinder, then there will be number of bolts. Here there is another bolt. The number will depend on this diameter of the cover plate. If you see the standard on pressure vessels, then this distance will have some minimum value. So this length P must be greater than some P minimum. So all these considerations will give you what are the number of bolts to be used here. Now once you use that, then F external is applied on the pressure on this cover plate. So each bolt will take the equal amount of external load. Let us consider that one particular bolt takes this load F external, although we mean that F external is actually the load taken by the entire cover. Now based on that, we can find out what will be the new load on the bolt. New load on the bolt, what we can do is that we can find out again we draw the free body diagram of the cover plate. So this is the cover plate, and we have this force F fasteners say, and here F joint, and this is F external. So therefore we have one equilibrium equations, that is Fj plus F external minus Ff is equal to 0. But this is not sufficient to calculate Fj and Ff separately. Fj is the force experienced by this joint, that is the gasket force. We make then, this is statically indeterminate problem, then we will have to use the kinematic relationship. Now we consider the bolts to be flexible, that is it has some longitudinal flexibility along the axial directions. So if you consider that, then the total extension due to the external force that is Fj or Ff will be equal to F initial, and this is again extended, that is there is an extension. If you say Kf is the spring constant of the bolt, then definitely the bolt acts like a spring because it has some longitudinal flexibility, and this is the delta is nothing but the deflections of the bolt. Similarly, the joint will be F initial minus K joint times delta. So here the kinematic relationship is that delta is same in both the cases. So the amount by which the gasket is inflated is the amount by which the bolt is stressed, the bolt is elongated. Now if you consider this, then these three relations will give you the value that Fj, if you use that, Ff will be equal to F initial, and delta is nothing but, if you calculate, then delta will be equal to F external divided by Kf plus Kj. So if you use that, then this becomes Kf divided by Kf plus Kj times F external. So this is the relation which we get. Now you can write this F initial plus 1 upon 1 plus Kj divided by Kf times F external. What we see here, that this is a factor F initial plus C times F external. So here we have a factor C which is multiplied with F external. So therefore all the entire load is not taken by the fasteners, but only take a part. Now if Kj is much larger than Kf, that is the joint stiffness is too large, then of course this terms goes very high and C becomes very low. In ideal situations we can have C almost equal to 0, and that is when there is no gasket in between, then Kj is very large compared to Kf, and it can have a very small value. C can have a very small value, but it then one can see that by having a very small value of C, one can apply a very large value of F external. That is, we can, if we have C is 0, then we can apply infinite amount of external force, but that is in fact not true, because this statement what you are seeing here, this one, this is true to some extent. If delta is too large, then Fj becomes negative, but Fj cannot take any negative load. So therefore we can have an upper bound on delta, and that means the upper bound on F external, as you can see from here. So therefore we cannot apply any arbitrary amount of load here, but we have to apply the load such a way that the gasket joint contact does not get loosened. These are the considerations we will have to give. Now how to calculate this Kf? Kf, we can use the very known formula, that is, we can consider this to be a rod. If we apply force, then the deformations, so delta will be equal to F times L divided by EA. So therefore, Kf is almost equal to EA divided by L. But what about Kj? Kj, calculations of Kj is very complicated. When you have a gasket joint, then the other parameters, that is, remember that there are other elements. If you consider the last example, there was the cover plate, then gasket, and then this one. So the entire joint stiffness is based on this entire combinations, and the gasket being very softer material compared to the other materials, so the entire stiffness will be due to the gasket. But really, whenever there is no gasket, then calculation becomes tremendously complicated. What we can take, that we make some simplifications, and we take a first term. For example, here these are the two plates, and we have a bolt here, so now when you take the joint stiffness of this combinations, then we take, instead of the plate, we take this frustum. Forget about the entire plate, but only take this amount and consider the stiffness based on this part. This also becomes complicated. Exact analysis will give very cumbersome results. Normally in the design, you make use of some empirical relationship, that is some experimental values of C. So what we are going to see now, the C, they are measured, C's are measured experimentally. In the next slide, we are going to see the various values of C for various kinds of joint. Now, this is how the bolts are to be designed whenever there is pre-stress. So we have F is equal to F initial plus C times F external. We calculate sigma based on F, and all other relationship for the pre-stress pre-stress will be equal to same as that without pre-stress. Now we are going to see some of the values of C. Now for metal to metal joint, you see, then this joint becomes very steep, and the compliance, that is Kj, becomes very high compared to Kf. I'm sorry, this is Kj, and therefore C almost becomes 0. For the narrow copper ring, we have 0.01. For lead gasket with stars, we have 0.10. For soft copper gasket, it is 0.40. For copper asbestos gasket, it is about 0.60. Soft gasket with bolt, it is 0.90, and soft gasket with stud, this is 1. Now these are the values used while designing the joints, that is designing the bolts with pre-stress. Now let us calculate what are the types of stresses introduced in preloading. What we see is that the tensile stress is introduced, of course, that is very obvious. Sometimes the preloading introduces shear stress, because what we see here, there are two plates which are to be joined, and the bolt is there. Okay, and we tighten it, we give a torque there. So if you consider this surface, then there will be some frictional torque acting, frictional force will act, and that will cause the frictional torque. If you draw the free body diagram of the bolt, then it looks like so this part here, what we see is the frictional torque acting. So you can give external torque, T external, for the tightening, and that will cause this Tf, which is equal to frictional torque. So if you calculate the shear stress due to torsions, then of course you will have some non-trivial value. So each point will be subjected to some shear stress because of this frictional torque developed between the two meetings, the meeting surfaces, that is the surface between the contact points between the bolt and the surface. Then there will be other stress, which is the bending stress, and that occurs whenever we have two misaligned or non-parallel surfaces. Now what we are considering, suppose we want to join one plate with the other. Now unlike the previous situations, here we consider that this plate is not properly aligned. So there is some angle alpha between these two, and we use a bolt and tighten. Definitely while tightening, the bolt will bend okay. So there will be a bending stress developed. What will be that bending stress? Let us calculate. Suppose the bending moment is m, and this angle here is the alpha. So therefore we have this famous relationship, that is EI del to W del x square is m, which while double integration gives EI W is m x square, where we measure x from this point. Let us say x is measured from this point. So mx square by 2 plus c1x plus c2, and we have this boundary conditions, that is at x equal to 0, w equal to 0, that gives c equal to c2 equal to 0, and this is again clamped at this end. So therefore at x equal to 0, w prime is equal to 0, this gives c1 equal to 0, and we are left with these expressions. Now the slope at x equal to L, slope is equal to w prime, where w is this displacement from this axis. So this becomes ml divided by EI, and that is approximately equal to alpha. So once alpha has some value, then we can get m to be alpha EI divided by L, where L is the length. L is the length of this bolt. Definitely what we see here, that because of this bending, a bending moment is developed, and this bending moment causes a bending stress. The bending stress again is given by the famous formula, that is sigma bending is my by I. So, a bending stress will be developed when we have misaligned surface. This is very important because the bending stress may be very large, so that the material may fail. So, we have to ensure that these two mating surfaces are parallel, and if it cannot be ensured, then we sometimes use spherical washer. So, sometimes we use spherical washers. Okay. These are sphere like hemispherical washers, and very effective for that purpose. So, these are roughly the number the different kinds of stresses introduced while preloading. Now, design of bolts for dynamic loading. Here the dynamic loading, this is very important, and when we design the bolts for the dynamic loading, then some important data are to be considered. The first one is the stress amplitude and mean stress. That is very important, and you have already learnt about it in the design of strength. That is, whenever we have a stress which is fluctuating, something like this, and this is varying with time, this is sigma, it has some maximum value sigma max and minimum value sigma mean. Then a mean stress is developed as sigma max plus sigma mean divided by 2, and amplitude, stress amplitude, sigma amp is sigma max minus sigma mean divided by 2, and we have various fatigue failure criteria based on this sigma mean and sigma amplitude relationship. Then the next is the fatigue stress concentration factor. Normally for the ductile material, fatigue stress the stress concentration factor is not very important, but for the brittle material it is very important. For ductile materials it is not so, because the plastic deformations will take place which will reduce the stress concentrations anyway. But whenever we have fatigue loading, then we have to take this fatigue stress concentration factor. So this is again tabulated. We have for various kinds of bolts, we have various fatigue stress concentrations factor. Then the corrected endurance strength. Corrected endurance strength. The endurance strength we all know, sigma E, but it is measured for some particular type of experiments, namely the bending experiments, but for different kinds of loading we will have different factors. So there are few factors. One is load factor, then maybe the surface finish factor, maybe the temperature factor. So everything has to be taken care, and we will have to get sigma E prime, which is the corrected value of this endurance strength. Then the yield strength or ultimate strength, this is of course very much needed, and the factor of safety. So this data must be supplied to the designer. Once these data are known, then of course we use various criteria. That is, suppose we know sigma max, sigma mean value and sigma amplitude, then there is an endurance diagram where sigma mean and sigma amplitude is plotted. Then there is one line which is known as the Soderberg line, and that line here, so this goes up to SY, the yield strength, and this is SE. When we have a factor of safety, then there is a factor of safety, we get to SY prime and SE prime. So the design must be such that it falls, any design data will fall on this line. So therefore, we have this relationship, that is sigma mean divided by sy prime, which is equal to sy divided by factor of safety plus s sigma amplitude divided by se divided by factor of safety is equal to 1. And now here we will have to introduce this fatigue stress concentration factor over here. So this is the relationship which we use. There are other relationships known as Goodman's line or Gerber's line, but Soderberg's lines are most often used, and this relationship will give you the value of different things like the, if you want the factor of safety or the area of the bolt, you can calculate with the help of this line. We will discuss more about that in a later lecture devoted entirely to the variable loading. So now the fatigue stress concentration factors, these are the fatigue stress concentration factor for metric grade. This is 3.5 to, for metric grade 3.5, 5.8, it is for the roll thread, it is 2.2 for the cut thread, 2.8, 2.1 for fillet, and so on, 6.6 to 10.9, this is 3.0, 3.8 and 2.3. Then we have the fully corrected endurance strain. These are roughly the some guidelines. ISO 8.8 M16 to M36, it is 129 megapascal. It increases as you go, increasing to ISO 12.9, where it for M1.6 to M36, that is for the metric grade 1.6 to M36, it is 190 megapascal. These are all to be found out in the handbook. Now there's a small homework problem given. The homework problem looks like here. The cylinder head of a steam engine is subjected to steam pressure of 0.7 megapascal. It is held in position by 12 bolts, which will take equally the entire load. Soft copper gaskets are used. Remember, for the soft copper gasket it was 0.4 to make the joint leak proof. Now in this case, of course, we have the initial force, and this is to be found out using this relationship 2.2840 D. Now these are used to make the joint leak proof. If the effective diameter of the cylinder is 300 millimeter, find the size of bolt so that the stress does not exceed 100 megapascal. You will have to use different data supplied to the design handbook, or you can use the data from this lecture itself. The answer to this homework problem will be given in the next lecture. So now we come to the end of this lecture. We have discussed how to design a bolt for the static loading as well as for the variable loading. For the static loading, we had the pre-stress, and sometimes we didn't have the pre-stress. The advantage of pre-stress being that the bolts will be relieved of the external load to some extent, but we cannot at our will we cannot increase this external load, because in that case the contact will be loosened and the load will again increase in the bolt. For the variable loading, we have used Soderberg's line, but there are other criteria possible. We will use them in some more details in a later chapter. So we come to the end. Thank you very much.